Good afternoon, everyone. This is Danielle Sass-Burnett with NARUC, part of the NARUC-NASIO Task Force on Comprehensive Electricity Planning. We are going to give folks another minute or two to join, and then we will get started. Good afternoon. This is Danielle Sass-Burnett with NARUC Center for Partnerships and Innovation. We're about to get started with the NARUC-NASIO Task Force on Comprehensive Electricity Planning webinar on distribution planning criteria. We've got a few dozen folks on, so we're going to provide some introduction and background context, and then we'll get going with our speakers. So as most of you who are calling on know, the NARUC-NASIO Task Force on Comprehensive Electricity Planning has been operating a webinar series since the summer. In May, a monthly effort. The topics chosen for the webinars have been based on feedback that we received from task force members. All of the webinars have been recorded, and they will be posted within the next few weeks to the task force website. The final webinar in the series before we all meet at our workshop next week is today's on distribution planning criteria. We are happy to have Steve Olia from the Arizona Corporation Commission and a task force member moderate the webinar for us, and he will introduce Patrick Dalton and Tom Minna of ICF in just a moment. Throughout the webinar today, you are invited to provide any questions by typing in the chat box or virtually raising your hand. Patricia DaCosta from ICF and I are viewing all of it, and we'll be happy to verbalize your question or call on you and unmute you if you'd like to speak. We'll be taking questions at the end of the presentations, but there will be plenty of time for Q&A. I'm going to turn this over to Steve in just a moment. Steve Olia has been at the Arizona Corporation Commission for 32 years. He served as interim director of the Safety Division, the chairman's designee on State Power Plant Transmission Line Siting Committee. He's been involved in reconstruction cost studies, cost of service studies, used and useful rate-based studies, et cetera, and was involved with several NARUC staff subcommittees. In 2017, Steve was asked to come out of retirement and return to the commission to serve in his current role as policy advisor to the commission chairman, Bob Burns. Since 2015, Steve has also been a member of the faculty for NARUC's Rate School, and we're so grateful that he's also been a member of the Arizona team under the task force. Steve, please take it away and lead us through today's event.
Okay, thank you, for having me, be the moderator, and thanks for that. And also, thank you to everybody that's listening in. And this topic of today's webinar, the distribution planning criteria, is very topical at this time because of all of the DERs that are coming into the systems. It's making the planning for all of the distribution systems more complex and more critical. So hopefully today's speakers are going to give some insight into that. And let me introduce our second speaker first. Tom Minna is a senior DER project advisor in ICF's Energy Markets team. In this role, he is responsible for supporting client objectives as the industry plans for increases in DER technologies. Tom joined ICF in late 2018 after spending 33 years with Consolidated Edison in New York, the last 5 years of which were on the Utility of the Future team, interfacing with technical and regulatory impacts of New York's Reforming the Energy Vision, the REV. Tom's experience includes overseeing the design and construction of electric power system designs to supply new business infrastructure in the New York City area, as well as emergency operations, control center operations, customer service, and electronic communications. Our first speaker is going to be Patrick Dalton. Patrick is a manager in ICF's energy markets team. He has 11 years of distribution engineering experience at a major U.S. electric and natural gas utility with roles related to operations and planning. Patrick led a team responsible for integrating DERs across the utility's service territory in 8 states. He also designed and implemented technology deployments for improving system reliability. Patrick brings experience evaluating grid impacts and developing solutions for load or DER connecting to the distribution system. Patrick, all yours, take it away.
Thank you, Steve, and thank you all for the opportunity to be here to speak with you today. So the topic at hand here is planning criteria, and I'd like to mention that there isn't one uniform set of planning criteria that's found at all utilities. If there was a survey out to 10 utilities of what their planning criteria is, it's likely that there would be some variation amongst those utilities in the exact criteria that are being reviewed during the planning process. So I'd like to start by grounding this in the overall planning process that's used for determining system needs during both normal and emergency situations. As part of that, there are overarching objectives. Reliability and safety are an example of some of those, which are really embedded throughout all of utility operations, including the planning process. And those objectives are translated into more specific planning criteria that are quantitative and can be used to evaluate solutions and prioritize solutions and evaluate risks. And then finally, we would like to cover how that plays into the distribution budget. So which aspects of planning criteria are related to budgeting and which are not. There are aspects of the budget that are sort of fixed in a way. And so we're going to spend a little bit of time differentiating how planning criteria affect some aspects of the budget and not others. Next slide, please. So starting with the distribution planning process, it's typically an annual cyclical process to determine incremental needs, and it'll start with a load forecast, which may include both top-down and bottom-up approaches. So from the bottom-up perspective, data is collected from energy management systems or perhaps even a person taking manual readings at a substation in order to develop historical baselines. And then factors such as weather or historic load growth and planned developments are included. At the same time, there's this top-down component where system-level forecasts are developed based on economic indicators, and those inform the high-level substation and circuit-level forecasts. The next step of the process is where the planning criteria starts to be introduced, and that's in constraint analysis, where planners are looking primarily at loading constraints based on the forecasts, but also included in that analysis are voltage and reliability criteria. So within the process, that's the first place that these criteria really enter. It's typically performed on a substation and feeder basis, the constraint analysis, that is. And if there are discrete or targeted overloads that are found based on that criteria, load can be transferred or the system can be reinforced. If there are numerous feeder or substation risks in an area, a planner may initiate a regional study to evaluate capacity and contemplate bringing in an additional source which may be a new substation. And that process can take years for all of the siting and permitting and planning. So it's important to identify those regional constraints early on. Once the constraints are identified, and this is typically done through a set of tools that will be covered in more detail at the in-person workshop next week. Once those constraints are found, solutions are identified, alternative solutions, in order to mitigate that risk. And there will typically be a range of solutions that could meet the planning criteria. So they can be assigned a risk score in order to evaluate. And within that risk score, here's another place that those planning criteria may enter. And then the next step is budget create. So based off of the solutions identified and the criteria used to prioritize the project, some are entered into the budget. And then finally, the process typically ends with design and construction to implement the solutions. And for distribution projects, that might take 1 to 2 years, and substation projects might be more on a 3 to 5 year timeline. Next slide, please. So next, talking about the objectives that are involved in that planning process. The 4 main objectives here are safety, reliability, cost, and then any other policy goals that might be relevant to that utility. Starting with safety, it's always a top priority to keep the public and utility workers safe, and that's built into the planning criteria by assuring that there is a safe level of power and voltage expected on the system under the reasonable range of conditions reviewed. Next is reliability, and this is an increasingly important objective to all types of customers. It's typically measured by standard metrics, and one of these is shown off to the right of the screen, SAIDI, which is an indication at a system level, the duration of an outage or outages over the year, that a customer might experience. Reliability objectives are achieved through a combination of programs aimed at asset health, system hardening, technology deployments, and capacity planning. And that last one, capacity planning, is the most relevant to this discussion here. And we are going to look at how that's really achieved on a system through the planning criteria and implementation of designs in the field that allow service to customers under both normal and contingency configurations. We will focus on a type of system that is very common across the US, where circuits can tie together to pick up portions of adjacent circuits. But I would like to mention that there are other types of designs, for example, in downtown, very dense areas. The system may be built with more redundancy, and a higher level of reliability would come along with that, potentially. And then on the other end of the spectrum, there are rural areas where some of the capabilities that we will be talking about for feeders picking up sections of adjacent feeders, it might just not be possible based on the economics of building out that infrastructure and the benefit that's anticipated to be achieved by those additional assets in the field. Next is cost, and this is a factor that's being optimized for each category of the distribution planning budget. For example, projects targeting capacity may also maximize reliability benefits. Many design constraints are typically alleviated by one of the solutions that might be implemented, referenced in the planning process on the previous slide. So utility planning and budgets are usually designed to drive least cost, best fit solutions during the project prioritization. And finally, regarding state policy, there may be other goals that are introduced into the planning process, for example, incorporating a certain level of solar or storage DER to meet state environmental or grid flexibility objectives. Next slide, please. So translating objectives, which are these higher level goals, into concrete criteria is sort of the focus here that we're going to be walking through next. And objectives are, I'll describe them as goals, high-level goals that are desirable system characteristics or attributes. That's what we were talking about: safety, reliability, cost, state policy. Whereas the criteria used by planners are more specific: voltage levels, loading levels in terms of electric capacity, and being able to serve that amount of capacity both in a normal and contingency configuration. And that's what we're going to look at next here on the next slide, is the three main types of planning criteria that might be found in common amongst utilities. The first, electric capacity, has long been the focus of planning processes, and the goal there is to be able to serve the peak load that customers may demand at any time during the year in both a normal, so a sunny day and the system is completely intact as designed, as well as contingency configurations or backup configurations that might result from equipment failures or the need to perform maintenance on a specific part of the system. So capacity criteria is really driven by physical thermal limits. All electric equipment carrying power is limited to a level of flow that assures the amount of heat produced will dissipate prior to that equipment experiencing loss of life or premature failure due to mechanical stresses of that heat building up. So kind of underlying this capacity concept is really a thermal limit. And those thermal limits are calculated based on industry standards typically, but there are some assumptions built into them. For example, what the ambient air temperature is, or for an overhead line, perhaps what the wind speed is to dissipate that heat, excuse me. So capacity is tied to reliability and asset health because the objective, the goal of this planning process is to assure that asset loading remains within limits at all times in order to prevent premature failure of that equipment, which could translate into degraded reliability. In terms of what planners look at in the process for electric capacity, it's typically the mainline feeders, so the trunk of the tree, so to speak, and large substation components. But other devices are also looked at in order to assure there aren't any weak points of failure there. When there is a limit encountered, planning process may reroute power to reduce flow across the element that was experiencing a potential overload, or to perhaps replace equipment, or increasingly with DER and non-wireless alternatives, there are other options that can be explored. In terms of voltage criteria, so the second bullet point on the list here, customer equipment is designed to operate within a range of voltages that correspond with utility planning criteria. And these are based on industry standards. Over on the right-hand side of the screen is an image that shows a source of electric power, the substation on the left, and then just a conceptual feeder where there would be customers distributed along the line potentially. And then at the very end is a distributed generation unit or DER. We could assume that this is a solar device. So underneath that schematic of the system is a simplified graph showing voltage criteria that a planner might look at. It shows the standard range of voltages that are acceptable. It's called out as ANSI range A. That's industry standard that's applied. And so there's two lines there, one showing before DG is installed or DER. And what you see there is a typical declining voltage profile. Everything is within limits that was studied by a planner to assure the voltage range was met. And then the other line indicates the potential impact of DER on that voltage profile. And so planners need to account for those changes being brought about by DER, where the voltage may be elevated above traditional levels and perhaps sometimes even outside of the range of acceptable voltage levels as defined by industry standards. So that's an important criteria also looked at. And then finally, briefly on the reliability side, this one is less explicit in the planning process, but nevertheless, it's an important consideration. Preventing overloads, as I mentioned before, contributes to reliability by protecting the health of the assets. It's also used in project prioritization is another place where it really comes into play. Next slide, please. So now we're going to start to look at a series of slides laying out an example of how utility planners may view the electric capacity criteria, which has really been at the heart of planning processes for many years. So what we're showing on the left-hand side of the screen is a conceptualized version of a system found on the right side of the screen. So on the right side, in the upper right-hand corner of that kind of 3D graphic, there's a substation source that may contain two transformers. We're going to call that the blue substation here. It has two transformers with feeders coming out of it. So this is showing on the right-hand side one feeder coming out, a pole line that's serving houses and businesses. Real substations that serve moderately populated areas typically have multiple feeders and perhaps multiple transformers. So on the left-hand side of the screen, that's what we're showing is this hypothetical blue substation that has two transformers and four feeders that serve a mix of residential, commercial, and industrial customers. So a feeder serving purely residential customers may have around 500 to 1,500 customers. A feeder that's serving a large industrial plant, it may be dedicated to that plant. And this is called a radial system sometimes because the feeder emanates from a source and goes in one direction or radiates out into the field, and it's not networked together, which would be the other type of system. When DER is analyzed, this is typically the configuration that's done during an interconnection study, and the DER may or may not be included in some of the abnormal configurations that we will look at in the next slides. So this system intact situation is sometimes referred to as N-0, meaning this is the normal system. There aren't any components that are out. Next slide, please. So here we start to conceptualize a little bit further. We took away the other feeders to simplify, and we're going to concentrate on feeder A. So we're not showing the houses spread out along that feeder anymore, but let's imagine that there are still 1,000 customers spread out on feeder A amongst these 3 sections. And what's going to define a section here is our devices that can open up or close. So we don't need to get into the details of devices, but they could be switches or breakers, and they might be operated manually by a person operating a handle on a pole, or this could be automated equipment. So that's all I'll say about that. But the important part is that we can break up this feeder into different sections, and different utilities may have different philosophies on how many sections constitute a feeder. In our example here, we're going to say that this feeder is loaded up to 75% of its maximum capability at peak load. So each section of the feeder is carrying 25% of that peak capacity of the feeder. And the reason why we don't load this to 100% in the normal configuration is this feeder may need to pick up a section from a different feeder. And so that's what we're going to look at next, how other feeders tie together when planners are looking at criteria related to backup or contingency operations, and how those sections are picked up, and that contributes to reliability and service to the customers. Next slide, please. So here we start to introduce other feeders that might be connected. I'll mention that the blue boxes along feeder A that are shaded mean that those are devices that are closed. So feeder A is on its own, feeding to the end sections 1, 2, and 3. And then these boxes that are white are open tie points that are at the ready should feeder A need to be picked up by any of these adjacent feeders. And the adjacent feeders in this case are feeder C is connected to one section, feeder W, another section, and feeder X, another section. So we've introduced another substation source here, which is fairly common. These substations out in the real world might be a mile or 2 apart, and they will have feeders that look very much like feeder A. They're sectionalized up into a number of sections, and each of those sections carries 25% of the feeder. So this is starting to get at the contingency configuration and how we can serve when feeder A is out. I mentioned briefly before that DER may not be studied for abnormal or contingency configurations. And that's repeated here. So as we go through these next two steps, we'll just keep that in mind. So next slide, please. So here we are looking at some sort of event that takes out transformer 1 at this substation. It could be a weather event on the transmission system or equipment failure. What's showed in gray now is equipment that's de-energized. So those hypothetical 1,000 customers on feeder A are now in the dark temporarily. So this is where the planning criteria for a single contingency, also referred to as N-1, comes into play, where these adjacent feeders, C, W, and X, were designed to be able to pick up a portion of feeder A and restore service. So let's look at the next slide, please. That's what we're showing here now, that feeder that went out of service was now broken up into 3 different sections as designed by the planning criteria, where we have those open points between section 1, 2, and 3. And then the connection points to these adjacent feeders are closed in order to re-energize and restore those customers that are on feeder A. So going back to that philosophy of the feeders each being loaded to 75% as a maximum during peak load, where that comes into play here is picking up an individual section. One of those 3 sections is going to add 25% to that previous 75%. And again, this is at absolute peak, which is how the system is planned for typically. And when you add a section of a feeder with a full another feeder, in this case, we get to 100% capacity. And that's the end of this example of how that electric capacity planning criteria is used to assure safety and reliability. And now I'll hand it over to Tom to talk about some budget and policy goal topics.
All right, thank you, Patrick. Can you hear me? I think good, right?
Yes.
Good, thank you. So I just wanted to go through, if you are on slide 13, state policy goals and drivers that are part of the planning process and that are impacting it. And so we thought we kind of bridge the gap here to think about some of the policy components as part of this conversation. So if you look at it from around the wheel here, energy conservation is a major driver. So many states are looking for conservation. That's through megawatt hour, kilowatt hour reductions. And the implications for that are also driven through some of the utility changes, and the utility's control of voltage is often part of that. Patrick talked about the aging infrastructure, the asset life of that infrastructure. That is a driver that is impacting the criteria that the utilities need to use. And I think what we're seeing in the IoT world, data and better tools are also a major driver. Can you get the tools necessary to get to the granularity to understand the system better so that you can deal with better tolerances and potentially change some of your planning criteria without eroding performance? So those are areas of importance. The scale of increase of DER is a major driver. And I think all areas are seeing that, driven by technology, driven by incentives and the like. So I think that's consistent. Patrick talked a little bit about safety, resilience, and reliability. Well, these are key elements because as we think about the criteria, the addition of new assets out on distribution circuits that are now supplying generation that typically were just loads are now potential impacts for that reliability and resilience. And the utilities are challenged with understanding what that change is going to look like over time. And as you think about some of the distribution system, Patrick talked about the fact that oftentimes power is delivered from the substation out to customers. As we think about the flexibility requirements of generation out on a circuit, The utilities need to react to the fact that these are changing environments and that there may be generation sources on a circuit when there was only one direction of feed at a prior time that they could control. So they may now have 10, 20, or 30 points of generation on a feeder circuit that originally only had one. And so the greater flexibility is required associated with managing that. And in some jurisdictions, there's discussions on non-wire alternatives, the ability to think about DERs in a planning solution versus just a utility planning and asset upgrades. So those are areas that are under consideration. A lot of those are predominantly pilots these days, but there's a lot of learning that's advancing in these areas folks can use. Next slide, please. So when we think about the change in the traditional planning process, Patrick talked about that process, the objectives laid out, safety, reliability, cost, and policy, and the predominance of criteria tied to the ability to supply power and capacity, the load, the amps on a circuit, and the planning and tools to see how much exists, and the tolerance of voltage, whether it's ANSI standards. Those are the criteria that we talked about, safety, reliability also from the standpoint of the frequency of outages and the duration. Those criteria are evolving. And so what we're showing here on the right side of this slide is the fact that there are needs that are changing in the planning process. We're seeing much higher levels of system efficiency requirements, that is the reduction in losses. The advancement of EE and DR creates a significant change in forecasting, and that plays into the planning process. The DER integration concepts, technically, how are they connected, the scale of their increase, and the implications on resilience. So emerging needs of resilience, very, very specifically related to some very large events that can occur, whether they're storm surges for coastal communities, ice storms, or extensive heat. Response to an event as such and some negativity and/or investigation can often result in new needs for resilience on top of what the utility is already doing. There are also requests for advancements in security, whether those are cyber or physical. Certainly the IT basis for an increase in cyber responsibility is increasing in time. So what's still yet to be decided, and we're talking about it across the nation, is the issue of what is the change in criteria. And so the utilities are slowly evolving that view as they deal with the increase in penetration. And so the interconnection area is a classic example of an area where it's first thought of that is the connection point to understand the technical implications that are going to occur due to those needs. Next slide, please. So what we're going to bridge the gap here is to think about some of the planning process to the budget in the utility and thinking about how they get compared. So on the left side of this slide, you'll see capacity planning. And Patrick has laid out how that's considered within the utilities. And oftentimes, these risk factors that he talked about does allow for some consideration of prioritization. But more as important in the budgetary cycle for distribution planning is concepts around the asset health of the utility assets. And so if you look through there, you'll see there are areas of consideration for corrective maintenance, the requirements to replace failed assets to maintain a normal system design, the concept of preventive maintenance, the ability to understand the asset health at a point in time and respond to it, hopefully before a failure event. The reliability-centered maintenance could be areas where the utilities are working with commissions and staff to look at the worst performing circuits in their inventory and those customers that are abnormally being impacted on those circuits. And there may be requirements to do specific programs for those circuits to advance their performance and create better customer excellence. There are also condition-based predictive maintenance. So the ability to monitor and control the quality of oil in an asset, whether it's dirty, whether it's leaking, the implications of that maintenance for a thermal or physical failure is something that is part of the maintenance process. And so that is also a program for consideration in the budget. On the next slide, please. And here we show these two areas, capacity planning and asset health, as they get considered during an annual or a 2-year cycle. And the capacity planning process that Patrick talked about is done usually after the peak load period. And then you've got asset health planning that's going on at the same time. They are both considered within the budget, and utilities have different approaches to understand and consider their risks and or their prioritization to come up with a final budget selection with a cut line that is essentially tied to the rate case and the programs that were agreed to and the scale of those programs in a rate case. And then you go into the cycle of actually deploying and replacing as part of the budget cycle, and then you start it over again. Next slide, please. So here are some examples that the utilities work with, considering budgets and the budget for capacity. And as you think about a budget for capital, there are two types of budget for the utility. That is their budget for capital expenditures and the budget for operations and maintenance. Under the capital expenditures, we've talked about a couple of areas today. And so on the right side of the pie chart, you'll see asset health, and that is the condition-based elements we spoke to, the areas of capacity that were tied to the planning criteria, and the reliability components, whether they were the SAIDI areas, as Patrick spoke about, or the implications of storm response and the like. Those make up more than 50% of the capital budget. And there is some flexibility in treating some of those expenditures. But there are other areas that go into the prioritization in the budget, and new service connections. Utilities are required to connect new customers, and there must be a budgetary process in place to meet that need. There are often mandates that are through commission as a response to the events that I had talked about before. They could be negative events, they could be storm surge concerns, and there are orders related to you must meet this target, you must replace X amount of assets. So those mandates are tied into the capital budget. The ability to keep a fleet and their equipment up and running is part of that process, and then there are smaller areas, not insignificant, but smaller in scale from a financial perspective. Next slide, please. The other area of the budget, on capital, is the area in red here that I talk about from the standpoint of discretionary versus non-discretionary spend. And what's important here is the fact that almost 50% of the utility budget really is very much non-discretionary. The ability to respond to emergency events, in this case, what's an example might be a substation transformer failure, and that transformer no longer being viable must be replaced. So the cost to replace that is under emergency, and is really non-discretionary to get the system back to normal operating conditions. You also have non-discretionary areas for municipal works. If governmental areas are installing new roadways and the utility assets are in the way, utilities typically have to move those assets out of the way, and that's often called municipal or interference work. And while it's not significant in the scale for the utility, it is non-discretionary. New business, as I mentioned, is non-discretionary from a standpoint that all new customers should be connected. And then there are a number of other areas. This is a 5-year example of a capital budget and the categories. And there are replacement categories tied to inspection. There are also risk reduction categories that get prioritized. And then there are areas of grid technology, it might be grid mod and IT systems, and system expansion work that make up the rest of the capital area. And so this shows you that a lot of the area budget is relatively non-discretionary, and certainly the capacity elements that we're talking about in the planning criteria play heavily into this discussion. Next slide, please. On the operations and maintenance side, that is not capital, not major asset replacement, you'll see also that there are quite a few areas of non-discretionary spend. The ability to respond to a customer outage is emergency-based items, and that's often up to 15% or more of a utility's operation and maintenance budget, but absolutely must be required from a standpoint of asset deployment, HR, human resource deployment to an outage, as an example. And then there's a number of areas that are shown here in magenta that relate to inspection programs. Inspection, whether they occur at the distribution level, the transmission substation level. And in those cases, the inspection programs are very much required as part of the asset health cycle. In some cases, they're mandated. In other cases, they're not. But in all cases, without the inspection cycle, the condition for asset health could deteriorate, and the implications for safety and reliability, which some of our key objectives, must be met. So they become oftentimes non-discretionary to some level. And then we have other areas of the operation and maintenance budget, which could be pole maintenance, safety and training of human resources, the grid technology. So if you're doing grid mod programs that are capital programs, oftentimes folks forget that there are actually maintenance requirements for all the grid modernization areas that get included, and those need to be included in the O&M budget going forward. And the planning resources that actually do the work, a lot of the planning work that's associated with customer interactions, that's all part of the HR resources that are in the O&M budget. Next slide, please. Well, the last slide for our conversation before Q&A today is to talk a little bit about cost effectiveness and the views on how utilities approach the rate case submittals and the type of programs and how they consider the prioritization of those programs. And as Patrick talked about with regards to the planning criteria, this is very similar in that utilities approach them in somewhat different ways. There's really no standardization, although there are very similar approaches. The ability to show the impact and risk that is being avoided through a capital program and or expenditure, could be an individual project expenditure, is a key element of showing that cost effectiveness in the rate case. So the DOE did work on DSPX. It's a decision guide around how to think about cost effectiveness methods and how to consider that across larger areas and jurisdictions. So there is an objective out there to try to put a framework in place for norms so that jurisdictions, utilities can think in similar ways on how to treat asset investment. And so the three areas that are being looked at, and one that might have a case where you really don't have an extensive benefit analysis on a financial basis, but I absolutely need to do the investment because it's necessary as a foundational element of the utility process. That might be done under a least cost best fit approach. And oftentimes, systems in the emergency operations, SCADA, the outage management system, you must have an outage management system to manage customer expectations during outage events. Those areas might not have as many bottom line results, but they absolutely are necessary. So utilities will try to put them in place using a least cost, best fit solution that fits into their existing IT infrastructure. Another area of benefit cost analysis is in fact using financial analysis for the cost and the benefits. Some jurisdictions have actually put in guidelines and regulations tied to benefit cost analysis, seeking to provide insights into the exact financial calculations that get used as part of the project management and the project cost consideration. So in those areas, they're using that to actually put financial and dollars behind some of the programs so they can stack them not only in risk, but also in financial cost and benefit. And then the last category is deemed opt-in. That is a case in which a customer wants added contingency capabilities. It might be a data center that is a very sensitive customer, and they want to pay for the type of planning criteria that Patrick talked about at alternate backup scenarios. And it may cost more to do that, and in that case, the customer pays a differential cost from what is normal service to this advanced contingency service. And so those are the type of considerations that are taken into the budgetary process, both in the capital programs and as part of the planning criteria. And that summarizes our material for today, and we'd like to go into the Q&A portion, if we could.
Tom and Patrick, thank you so much for that presentation. It was very informative. And before I ask the first question, Danielle, could you kind of remind people how they can ask questions?
Of course. Thanks, Steve. Yep, there's a chat box below at the bottom of the control panel for the webinar. You are invited to type in any questions. We will see them and be able to read them out. Or you can click next to your name on the raise hand button, and that will work as well. Thanks, Steve.
Okay. The first question I have is, and this is for either speaker, do you think that the distribution system planning criteria is going to need to either change or evolve in some way as more and more DER is added?
Yeah, I'll start. This is Patrick, and Tom, please feel free to add to this. I do think that the criteria is going to need to evolve to incorporate higher levels of DER penetration. One example is when we were looking at the normal and backup or contingency configurations, I mentioned that DER is always studied in the normal configuration during an interconnection review when that solar plant or battery or whatever it is originally connected to the system. But it's not as uniform if that DER is accounted for in the backup or contingency configurations. So as the system starts to rely on DER more and more for load serving purposes and to prevent overloads in certain circumstances under non-wires alternatives, it's going to be important that the planning criteria evolves to account for being able to keep that generation connected in these backup emergency or maintenance configurations so that capacity and voltage criteria are still met. So that criteria may look similar in terms of the voltage range, and we need to keep the capacity below the limit to cause thermal overloads. But incorporating that criteria and expanding upon it in that backup configuration is going to be important. And another driver that comes into play here is the increasing automation on the system to automatically reconfigure the system after an event or an outage. And so there isn't always human interaction in that to evaluate from the operations perspective, is any criteria potentially being violated? So some of those things that would be looked at in operations need to move into the planning realm to be able to accommodate the system being more dynamic and automated in the future.
And Danielle, is there any other questions that people have submitted?
Nope, you can keep going. We haven't gotten anything in from anyone else yet.
Okay. What are the utilities doing to reduce customer outages as DER evolution is occurring, and how does that impact the planning process?
Okay, Tom here. I'll address that. So, you know, this is an interesting process change because it does get impacted by the scale of DER connected. And so the utilities, the first wave of planning change the utilities are seeing is associated with the interconnection process. And so the utilities are looking at their current processes, and in some cases, stakeholders have driven that process to look at the speed at which an interconnection can be accomplished and the ability to reduce costs for customers in that. At the same time, the utility is looking at the implications to their planning and performance. And they want to make sure that the DER being connected at a point on the system isn't going to adversely impact customers. So in those cases, for larger systems, the utilities are changing their planning criteria to put control devices in front of some of those assets, the ability to remotely operate those devices in the event that the utility system is in an abnormal condition and cannot accept the generation input. They're also being put into place to understand the current output of the system and having sensing capabilities in those locations. And in some of that consideration, they also have to put in communication systems to do that. And in those areas, that is one way in which they're trying to reduce the impact of a local DER on other customers in the local vicinity. So as Patrick talked about, the impact of voltage at the end of a circuit because of a PV system, in his example, is a great example of where the utility in its interconnection process has to make sure that the power quality impact from a system isn't adversely impacting other customers. So in those cases, it may not be customer outages, but it may be in the performance of voltage in the vicinity and the potential impact on customer equipment.
Okay, and all of this with all of the DER being added and all that, you've got all the planning for the distribution, but you also now, I'm assuming this is going to affect transmission planning also. And as far as utilities go, I mean, do the distribution people talk to the transmission people, and how are the two now going to interrelate? Because it seems that the distribution system is now actually becoming somewhat of a transmission system with all the DER. So how does the two now work together?
Patrick, you want me to take that?
Sure.
Happy to do it. Okay. So, this is an area that is undergoing change. Several of the commissions and jurisdictions that have tried to address integrated distribution planning, the advancements of some of the criteria and items we talked about today, are looking at how to tie that into IDP or IRP for those areas that are vertically integrated, or some of the ISO-related planning. And so the ISO-related planning really needs to understand below a transmission node what's happening, not just the net load at that location, because there may be cases where utilities are operating distribution level programs at the same time that ISO systems are operating both programs, and in those cases they have to coordinate. The concept of a customer output or DER reduction on a point in a distribution system and the transmission node thinking that that reduction will occur based upon an ISO event, and it doesn't occur because the distribution event called for it 4 hours earlier, is something of interest. And so that is one example of a case where there needs to be coordination between transmission planning, ISO planning, and distribution planning, and the need to not just consider net load, but to understand the underlying disaggregation of loads and the availability at points in time. And so I think those are key elements that are seen. And we often see that the forecast, whether it's a system level or a granular level at the distribution system, also need to handshake, and that the understanding of the forecast changes and the locational area of the forecast is the same in both planning processes is important. Otherwise, they're dealing with apples and oranges, and therefore might come up with more varied and error-related results. Those are just two examples.
Danielle, do we have anybody that's asked a question?
Not. You all have been answering questions very thoroughly and providing a tremendous information.
Do we have time for one more, or where are we?
Yep, we've got 3 minutes left. Please go right ahead. You've got another one.
Okay. What are the utility frameworks for evaluation of competing budget priorities? There's always the budget thing.
Yeah, I guess I'll answer that. I talked about the budget elements before, and I think it's important from a standpoint of understanding alignment. So when the utilities think about budget priorities, they're looking at tying it to their corporate objectives. Those objectives might tie to customer excellence, employee, public safety, as Patrick spoke about, financial stability, cost controls related to available funding and customer impact, and risk assessment. And I think risk assessment is a key area where this plays in, because as the utilities consider the varied programs, whether they're tied to criteria planning or asset management, the risk assessment element allows them to stack them and their impact on the potential for an event or the potential for a high-scale, high customer impact event. And in those cases, scaling the risk assessment and tying it into other components of value are often parts of how the utilities consider their budget and how they tie in that budget. And that's why we brought in this conversation today into planning because we thought it really needed to get considered at the same time.
That's all I have on my end, Danielle.
Excellent. Thank you all so much. Thank you, Steve, for guiding us through a great set of questions. And to Patrick and Tom for a really informative presentation, as noted. This will be the conclusion of the webinar for today. We're right at the top of the hour. The webinar has been recorded, and we will post it and make it available to all the task force members and others. And we'll say thank you so much to everyone and have a great rest of your day.
Thank you, Danielle.